أوكي. نرحب بكم في هذه الأمسية في المنتدى الثقافي للجمعية الفلكية الأردنية. وفي الحقيقة يعني ضيفنا اليوم هو ضيف مميز جدا، البروفيسور توم جيبالي، من مرصد جيميني في هاواي. طبعا هو حصل على درجة البكالوريوس في عام 1967، يعني من زمان. وهو ودرجة الدكتوراه في عام 1974 في الفيزياء من جامعة كاليفورنيا بيركلي. طبعا كان تحت إشراف البروفيسور تشارلز ستونز. طبعا لاحقا تابع دراساته لما بعد الدكتوراه في جامعة يو سي بيركلي وجامعة لايدن ومرصد كارنيجي. أخذ منحة بمرصد كارنيجي في باسادينا، ثم انضم لتلسكوب يو كي اي ار تي بهاواي التابع للمملكة المتحدة عام 1981 كفلكي. وبين عامي 1987 و 1998 أصبح الفلكي المسؤول والمدير المشارك في مركز الرئيس العمليات الرئيسية في المرصد يو كي اي ار تي. تمام. انضم إلى مرصد جيميني كفلكي في عام 1998، وتقاعد في شهر جانيوري 2018. يعني هو حاليا متقاعد لكنه ما زال يتابع عمله في هذا المجال. اهتماماته البحثية تتضمن مركز المجرة، والفضاء بين النجمي، والغاز والغبار بين النجوم عفوا، وتشكل النجوم، والنجوم المستعرة والمستعرات الفائقة أيضا، والنجوم المتطورة غير الاعتيادية، والنجوم الأقزام البنية وسطوحها، وكذلك الأغلفة الجوية، وأيضا الشفق الموجود في كواكب النظام الشمسي، شفق القطبي يعني، والموجود في كواكب النظام الشمسي وأقمارها. وبالتالي نحن نتحدث عن شخص يعني موسوعي إنجاز التعبير في مجال علم الفلك، يعني اشتغل في مواضيع متباينة للغاية، وله أكثر من 1000 ورقة بحثية. Professor Tom Geballe, you are most welcome at the Jazz Cultural Forum. He's an emeritus astronomer at the Gemini Observatory in Hilo, Hawaii. He received his bachelor degree in 1967 and doctoral degree in 1974 in physics at the University of California, Berkeley, the latter under Professor Charles Stones. Following postdoctoral appointments in physics at UC Berkeley and at Leiden University and the Carnegie Observatory Fellowship in Pasadena, he joined the staff United Kingdom Infrared Telescope UKIRT in Hawaii in 1981 as astronomer, and between 1987 and 1998 he was astronomer in charge and associate director and head of operations at UKIRT. He joined the Gemini Observatory as astronomer with tenure in 1998 and retired in January 2018. His research interests include the Galactic Center, interstellar gas and dust, star formation, novae, supernovae, unusual evolved stars, brown dwarfs, and the surfaces, atmospheres, and aurorae of solar system planets and moons. He published more than 1,000 papers. Okay, Dr. Tom, you're most welcome once again, and you can have your presentation. And as you told me, you may accept some questions during the presentation, right? There's no sound.
In the end.
In the end, type. Okay, but I can't hear his sound. Okay, you have the floor. The mic, Dr. Tom, the mic. حاطط المايك.
Can you unmute me?
Yes, great.
Oh, coach, now you hear me. Good. Okay, thank you.
Okay, thank you.
If you put up the full screen, are you
Yes.
showing the full screen? Okay, because
Yes,
I only see part of it.
Yes.
Okay, well, thank you very much for that long introduction, and it's an honor to be speaking to a group of amateur astronomers and some other people. Actually, the last time I spoke to amateur astronomers was at least 40 years ago in Los Angeles. Amateur astronomers help professional astronomers a lot. I hope to get to the point where I can show you that. They monitor a lot of variable stars. Although there are now robotic telescopes that discover most of the supernovae, there are still some discoveries of new supernovae made by amateur astronomers. And that most recent one was very important. I just actually heard a talk about one that was picked up by an amateur astronomer who saw the brightness of an object in a distant galaxy brightening very, very rapidly over just a period of an hour or so. So amateur astronomers, in addition to enjoying observing on their own, are helping professional astronomers all the time. So yes, I'm on the other side of the world. It's morning here. It's about 5:35 or so. I want to tell you, my talk is going to mainly be about the Gemini Observatory, a lot of things about how it works, who are the partners, and so on. The outline of my talk is on the left of the slide. If there's time, I'll get to a little bit of science, but running this observatory is a very complicated operation, as you'll see. And so let's go on to the next slide, please. Okay, so Gemini Observatory is one observatory, but there are two telescopes. One of them is in Hawaii, where I live. The other is in South America, in Chile. And it is operated and owned by 6 partner countries, Argentina, Brazil, Canada, Chile, Korea, the United States, and the University of Hawaii, which isn't a partner country, but because the telescope is in Hawaii, the University of Hawaii astronomers get a 10% share of the time at Gemini North. Likewise, Chile is the host country for Gemini South, and it gets 10% of the time at Gemini South. The two telescopes are shown there. The top one is Gemini North on top of Mauna Kea, and the bottom one is Gemini South. You can see they're almost identical. Some of the instruments they have are identical, but others are very different. Okay, could we go to the next slide, please? I don't see it yet. Change slides, please. There we go. Okay, so I'm going to concentrate on Gemini North because that's the one I use most often, although I've been to Gemini South many times. So this is the location of Gemini North. It's on what we call the Big Island of Hawaii. The whole state is called Hawaii. As you can see at the top right, it's made of many different islands, and there are many even smaller islands, but these are the islands that have almost all of the people on them. Hilo is on the east side of the Big Island, and that's what you're looking down at. Hilo Bay is to the right, and then in the distance you can see a snow-capped Mauna Kea, which is a 4,200 meter dormant volcano. Let's take a look at the next slide, please. Oh yes, and then on the left, the offices of Gemini are over on the left of this slide, the Gemini base office. That's where we spend most of our time. And in fact, now the telescope is run remotely, so even in the nighttime, people are there operating the telescope. Okay, next slide. Okay, so there's a view of the top of the mountain. You can only see a couple of the telescopes. Peeking off to the left of the summit is, I believe, the Japanese National Telescope, Subaru. Gemini North is indicated with the arrow, and to the right of Gemini North is the Canada, France, Hawaii telescope. Now, the next slide shows you the top of the mountain viewed from above. And here you can see almost, I think, all of the telescopes. So starting from the left is UCURT, the United Kingdom Infrared Telescope, where I worked for 17 years before moving to Gemini. Just to the right of UCURT is the University of Hawaii 2.2 meter telescope. That was the first telescope built on the summit of Mauna Kea. Then Gemini is there, the 8.1 meter telescope. And then further along the ridge, the summit ridge, is the Canada, France, Hawaii telescope. And then further to the right, you can see a small telescope, the NASA Infrared Telescope Facility. And just beyond that, the two Keck telescopes, 10-meter telescopes. Those are the largest optical infrared telescopes on Mauna Kea. And then next to them is the Subaru 8.2-meter telescope. And then down below the summit, there are some sub-millimeter telescopes, the James Clerk Maxwell telescope, which was built by Canada, the Netherlands, and the UK, but is now operated by the Eurasian Observatory, which I believe is mainland China, Taiwan, Japan, and Korea. And then to the right of that is the sub-millimeter array, 8 telescopes, 8 sub-millimeter telescopes, each one 6 meters in diameter, and they're situated to the right and down below the Keck and the Subaru telescopes. You can barely see them in this image. And then off of the summit, quite down, if you look at the bottom left, is the largest telescope on the mountain, the very long baseline array telescope, a 25-meter telescope that works with other telescopes scattered around the world to get very high resolution images, radio images of objects. Okay, next slide. So it's a very busy site. Now, here I want to tell you a little bit about why Mauna Kea is one of the best sites in the world for astronomy, and there are many reasons. First of all, of course, the weather is clear most of the time, or at least more than half the nights are totally clear, which is almost a prerequisite for any big telescope these days, or any observatory. The sky is dark. It's not lit by city lights or street lights. We have a very good street lighting ordinance law that means that street lights have to be shielded from the top. At the moment, most of the street lights are low pressure sodium lights, which only emit at 2 wavelengths at the sodium D line. So the rest of they look orange, and some people don't like them, but they're very helpful to astronomy in that they only brighten the sky at those 2 wavelengths. And actually, most of the time, the towns down below, they're far away and they're often covered by clouds at night. So it's very dark on Mauna Kea. Mauna Kea is located near the equator. That means it can observe a lot of the southern hemisphere and all of the northern hemisphere. Fourthly, a very important one is that it's located in the middle of an ocean with steady trade winds. And that means that generally there's a very smooth flow of air over the summit. And that means that the image quality is very good compared to continental sites. And on a continent, the sun shines down on the ground during the day, warming up the ground during the night. The ground cools. That leads to warm air rising, creating turbulence in the atmosphere, and that makes the images not as good. That blurs the images quite a bit. But because Mauna Kea is in the middle of an ocean, the sun can shine down on the ocean all day, doesn't really change its temperature. And so once the sun goes down, the seeing stabilizes and often becomes very good. Sometimes we get natural seeing as good as 0.2 of an arc second. Sort of a typical seeing is more like 0.7 of an arc second, but sometimes it gets as good as 0.2 of an arc second. Because Mauna Kea is high, it's cold at night. You can see there's sometimes snow, and it's usually down at 0 Celsius at night, or even below that. And that means that the instruments are cold, the atmosphere is cold, warm things emit infrared radiation. So the fact that it's cold there is very, very good for infrared astronomy. So it's one of the best sites in the world for infrared astronomy. And finally, because it's in the middle of an ocean and there's a very stable flow of air, the water vapor drops out of the high altitudes and goes down to low altitudes and is trapped there by an inversion layer. So it's very dry above the summit, and that also is very good for infrared astronomy. But what it means is that it's wet down at sea level, especially on the side where I live. Hilo gets 300 centimeters of rain per year, and there's some places a little further, higher altitude, not as high as the mountain, that get more than that, 400 or 500 centimeters per year. So it can rain very hard here. And in fact, where I live, we often have streams running across our property when it rains very hard. Okay, next slide. Thank you. Okay, well, the weather's awfully good most of the time on Mauna Kea, but it's not always good on Mauna Kea. Here's some examples of bad weather. At the top left, you see the result after or during a big snowstorm that left, I think, I don't know, 15 or 20 centimeters of snow at the summit. And that stopped observatories from operating for a long time, because if they get snow on their domes, then they can't be opened and used. There also are lots of cloudy nights, like the one at top right. There are not frequently, but there are occasionally nights where we get freezing fog. And so the whole mountain gets coated with frost. And of course, when that's happening, we cannot open the dome. We have to keep it closed to protect the telescope mirrors. And we also have hurricanes occasionally, although generally the water around the Hawaiian Islands is rather cold or cool. So the hurricanes often approach the islands. You can see they're much bigger than the islands, but they often sort of die out as they approach, although there occasionally has been a full-scale hurricane that's hit a couple of the islands. The Big Island has somehow escaped that over the time I've been here. There's not been a full-scale hurricane, although we certainly have had tropical hurricanes that have degraded to tropical storms come across the island and dump lots and lots of rain on the mountain and on Hilo. Okay, next slide. Okay, so this is going to be a time-lapse video of a good night on Mauna Kea. So if you can run that, so this shows the Gemini and shows the Canada, France, Hawaii telescope in the background. You can see at times we use the laser for helping to sharpen the images. I'll explain how that works a little later. The moon is out, so the sky looks rather bright. You can see there's not hardly any lights down below. The moon is now set just before sunrise, and now it's sunrise. So that was about a 10 or 12 hour video, all in the space of about a minute or so. Next slide, please. Oh, there we go. Okay, so this is a different night. When the weather wasn't so good, you can run the video for this. There was a thunderstorm, big patch of thunderstorms over the Hilo side. We're looking east. So you'll see a lot of flashes from lightning. Now you can see Hilo, and you can see a road going between the east and west sides of the island. You can also maybe see planes taking off, going off to the left. You see these streaks of light occasionally going to the left. Those are planes leaving from Hilo, probably going to Honolulu on another island. Hilo is pretty bright, but these are all time exposures, so you can see. So it's really not really brightening the sky above Mauna Kea very much. And in addition, the moon's up, so that's the main source of brightness. Here comes the sun again, yes. Okay, next slide, please. Okay, I just wanted to show a couple of slides. It's really beautiful on Mauna Kea. When it is after a snowstorm, it's gorgeous. This is a view from the summit cone of Mauna Kea. Mauna Kea is a dormant volcano, and at the summit there are a whole bunch of cinder cones from the end of the eruptions, which the eruptions ended about 10,000 years ago. But there's this beautiful cone that's to the south of the summit, and then if you look in the distance, you see Mauna Loa, which is almost as tall as Mauna Kea, much, much bigger. It actually is the largest in volume. It's the largest mountain in the world. Next slide. Another amazing sight that you see from Mauna Kea on a clear evening is as the sun goes down, the shadow of Mauna Kea rises up into the sky. So there's actually a shadow in the sky. That's what you're seeing. Again, we're looking more or less southeast. The bay there you see is Hilo Bay, and Hilo is just to the right of that bay where I live. So there are wonderful sights to see, and every night there are tours of Mauna Kea at sunset, and lots of, say, 100 to 200 people come up to the summit to see the sunset, see the telescope domes open, and then they go down and leave the site dark again. And astronomers can go ahead and do their work without worrying about headlights and so on. Okay, next slide, please. All right, so let's explore the Gemini telescope a little bit. The Gemini North and Gemini South telescopes are actually basically identical. Each one is a 8.1 meter diameter primary mirror and a Cassegrain alt-az mount. The instruments are mounted at Cassegrain, which is F16. The mirrors are very thin. They're what are called meniscus primaries, which means that they flop under the, due to gravity as the telescope tips, they would flop, but they're all actively supported by actuators, which push on the bottom of the mirror, and the shape is adjusted once per minute by a monitoring system to keep the shape the right shape. The other thing is that the mirrors are silver coated. Most telescope mirrors are aluminum coated, but silver actually optimizes the infrared as slightly more reflective than aluminum coatings, which are hardier than silver. So it's a little more fragile. We have to take very good care of of the mirror, make sure it isn't exposed to water vapor and so on, to maintain it for a while. And I'll show you later how the telescope gets recoated after several years. We take the mirror out and put a new coating on the mirror. The instruments are mounted below the primary mirror, on the bottom of the primary mirror cell. You can't see them in this view. The dome has one feature of the Gemini telescopes is that the dome has adjustable vent gates. If you look at the bottom right, you'll see that the dome, although it's open, there's also these vent gates that open up, and that allows the primary mirror to maintain its temperature at the same temperature as the outside temperature and adjust very rapidly if the temperature changes. And that's very important because if say the telescope were colder than the outside, you might get water vapor condensing on it. If it were warmer than the outside, then there would be warm air rising off the primary, and that would lead to a little bit of blurring of the images and reduce the seeing. It's because the telescope's very lightweight, it's very subject to wind shake, and so those vent gates can be adjusted, or they can be fully closed if it's too windy. So there often are nights where it's windy, we can still observe, but we have to just live with the slightly poor seeing that we would get if the vent gates were open, because we don't want dust to get on the primary mirror. Next slide. Okay, so underneath this is if you tip the telescope over slightly and you walk down to the floor, then you can see the instruments which are mounted on side ports. There are 4 of them mounted on side ports, and they can be fed by the light from the telescope by a diagonal mirror which is in the middle and can be rotated to switch the light from one instrument to another. So it gives Gemini a lot of flexibility in terms of what we observe. We don't have to observe with one instrument on the telescope at all night. We can switch from one to another. And there's a bottom port as well, where the instrument is up looking, and in that case you just slide the diagonal mirror off to the side, and then the light reaches that instrument. Now, normally, as I said, there are 5 places for instruments. Normally 2 of them are taken up by not cameras or spectrographs, but by other units. There's a calibration unit with thermal sources for flat fielding and arc lamps for wavelength calibration. There's also an adaptive optics system, which I'll explain later on. So those take up 2 of the ports. So we normally have 3 cameras or spectrographs available, and there's actually a place for a 4th small instrument, which is a speckle instrument that gets snuck in up above those instruments. So we actually can have 4 instruments available at any one night, which gives us a lot of flexibility in terms of what we do, and it's really key to how how we operate the telescope. Next slide, please. Okay, so I just wanted to show you a little bit about some of the instruments. So at the bottom right are 2 output images of the visible instrument. We have one visible instrument which does many things. It's called GMOS. It takes images and it takes spectra, and it takes spectra in many ways. You can use a long slit if you say you want to observe a galaxy. You put the slit of the spectrograph along the galaxy, and you get spectra on the array along the galaxy. It has a multi-object capability, and that's illustrated sort of in the middle, in the right hand of those 2 images, where you set up, we can make masks with slits positioned in the mask at different places that correspond to the locations of objects that want to be observed, that the scientist wants to observe. So the scientist will take an image of the field, and that will help us design a mask that allows us to get spectra of different objects. So instead of having a long slit, there are lots and lots of short slits, each one positioned at the position of, say, a galaxy or a star, and so on. And then it also has what's called an IFU spectrograph, an integral field unit spectrograph. And in that mode, a region of the sky, a small region, say of maybe 5 by 7 arc seconds, is split into many different pieces and rearranged onto the long slit of the spectrograph, and then you get spectra of a sort of a continuous region. So, for example, if you were studying say a galaxy, the center of a galaxy, you could use the integral field spectrograph to get spectra all around the center of the galaxy, rather than just putting a long slit across the galaxy and just getting a spectrum of the outer parts of the galaxy and a little bit of the center of the galaxy. So those three options plus the imaging option make it a very powerful instrument. In the infrared, we have separate cameras and spectrographs, and I'll just show you the one that I've been most involved with. That's called GENIRS, the Gemini Near-Infrared Spectrograph. It doesn't take images, although it has a small imaging mode for acquiring the object, but it produces spectra. And the one I'm showing you on the right is just a 30-second exposure of a planetary nebula, which maybe some of you have observed as a fairly bright planetary nebula, NGC 6572. And this spectrograph gives you a full spectrum from 8,000 angstroms to 25,000 angstroms. And if you look sort of in the center of those stripes, you see a bright strip. That's the continuum from the central star and the very brightest central region of the galaxy. But then those horizontal lines on each of the stripes are spectral lines due to elements like hydrogen, helium, oxygen, carbon, and so on. And they're just, you can see there's a huge number of them. And analyzing those tells you a lot about the conditions of the gas in this object. So spectrographs are very important. That's what I hardly ever have published data with images. Almost all my papers have to do with spectra of a variety of objects. And yeah, and likewise, GMOS and some of the other instruments that we have can do similar things, provide spectra that tell us a lot about the physical conditions in the objects that we're observing. Okay, next slide. All right, so this shows 4 of the large telescopes on Mauna Kea have laser guide star adaptive optics. Now, adaptive optics is a way in which the images of objects can be sharpened, and of course that's what astronomers want. They want to be able to get more detailed images of objects, and to do that, even though the seeing is very good on Mauna Kea, it can be made better with adaptive optics, either using a bright star near the object that's being studied, or if there is no bright star, using a laser to produce a star. That then can be whose shape can then be analyzed quickly, and the deviations from a sharp image can be fed back to what's called a deformable mirror, and that mirror can be adjusted rapidly to correct for the blurring of the blurring of the images. So let me show you how that works. I think the next slide shows that. Okay, so go ahead and run the movie. So on the Gemini North and South telescopes, there are, actually, if you go back to the previous one for a second, I forgot to mention something. Yeah, okay, so at the bottom left and right, at bottom left, somebody took a picture when both Gemini North and Keck were both observing objects in the center of the galaxy, and you can see the laser beams pointing up to the same place in the sky, right near the center of the Milky Way. On the right, I just wanted to point out that Gemini South has a laser system with five beams of light, separated by, I think they're separated from one another by about 1 arc minute. And using that system, you can actually sharpen the images over a wider field of view. Out in space, the Hubble Space Telescope gets sharp images over its entire field of view. These adaptive optics systems that we can use at the ground cannot do that, but they can only get sharper images than HST over small fields of view. But by using more laser spots, you can widen that field considerably. So Gemini South is the first telescope to have that kind of a system in place. Okay, now let's go back to the movie. Okay, go ahead and run it. So here's the bottom of, this is the bottom of one of the Gemini telescopes. And mounted on the telescope is a laser. That laser is tuned to the wavelength of one of the sodium D lines at 5,890 angstroms. So the dome opens. Telescope points to the object to be studied. If it's a bright star and you want to study the region around the star, that star could serve as the star for adaptive optics. But if there isn't a bright object there, then what we do is we project a laser up into the sky. There it goes up, and at about 90 kilometers above the Earth, it runs into a layer of atmosphere that has sodium ions from meteors, and so on that have been left in the atmosphere, and those sodium atoms, they absorb and re-emit the light, some of which goes back down to the telescope, and so it looks like a star when you point the telescope and you turn that on. You see a bright spot. Okay, now what happens with that spot? Telescope picks it up. So the light reflects off the primary, goes to the secondary, and goes down in through the hole in the primary. And as I mentioned, one of these ports has an adaptive optics system in it. And now we're going to see that. And so in that, you'll see what happens is the light from the infrared object that you want to study is there as well, and the laser light is there. The laser light goes straight through that diagonal mirror. The infrared light goes into the instrument, say the imager, and this is what you would normally see. You'd see that's when you'd see this blurry wandering structure because of the atmospheric turbulence. And what the atmospheric turbulence does is it means that the wavefronts of the star or the laser are distorted. Now they go into a sensor that determines the nature of the distortion, and that gets fed back to a deformable mirror, which changes its shape to flatten the wavefronts. So now that they're flat, they go into the instrument, get focused sharply, and when you turn it on, and when they reach there, then you get a much sharper image of the star with diffraction rings. It's really quite amazing. So that deformable mirror has to adjust very, very rapidly because the turbulences and the blurring on the light path changes very rapidly. And so we normally run it at 1,000 times per second. That means every thousandth of a second, the camera looking at the laser or the natural guide star takes an image, analyzes its shape, and then feeds back information to the deformable mirror, which then adjusts. And then a millisecond later, the same thing happens. So it's adjusting itself all the time. And that leads to much sharper images than we can get from the ground, and those that rival or even exceed the image quality of the Hubble Space Telescope. This is a system that currently only works at infrared wavelengths. At visible wavelengths, the deformable mirror would have to have much finer control over many more actuators to change its shape on a much finer scale to correct, and that technology is not yet available for astronomy, but it works very well at infrared wavelengths. Okay, next slide. Okay, now I want to talk about how we observe at Gemini. Now, when I was a graduate student at Berkeley, and for many years when I was working at UCURT and other places, telescopes were operated in what's called a classical scheduling method, in which various programs were awarded time and they were allocated specific nights, and the visiting scientist would show up at the telescope and would hope that the weather was working and that the telescope was working and the instrument was working at that time. If not, you were just out of luck. There might be a wide range of programs that were given time, some of which were very important and others at least judged to be very important, others which were judged by the committee that allocated time to be less important. But each one had the same probability of being successfully observed. So you could have the highest ranked program, and if the weather were bad during the nights you were scheduled, it's just too bad. You'd have to come back and observe maybe the next year. You can't say, well, my program was weathered out, so I'm going to hang around the telescope and observe it at a later time when the weather's good, because other people were scheduled on those nights. So Gemini introduced a system called Q scheduling, which basically is a different way of scheduling the telescope. And that is that successful programs were observed not on specific nights, but in order of scientific priority, more or less. And the Gemini staff do most of the observing. So depending on the weather conditions or so on, the programs would, the general philosophy would be to do the highest priority programs that are consistent with the weather conditions. And that those change from night to night. But the result of that would be that the programs judged to be the highest priority would have a higher chance of being completed than the lower priority programs. And Gemini has been using that system since it was built in around 2000, the two Gemini telescopes. Okay, not all programs are run that way, but most of the programs are run that way. And I'll give you a little more detail next. So if we go to the next slide, I think. Yeah. Okay, so each proposal for telescope time has to choose a type of observing. There's the standard semester program where you just apply for, say, I don't know, a certain number of hours of time. That 60% of the time at the telescope goes to those. There's poor weather programs where you can submit programs to observe very, very bright objects when the weather's bad, programs that might not be very high priority. For example, I had a program that ran over several years to look at bright stars in the galactic center, seeking to find stars that were suitable for another program. That program ran for years, and over a five-year period, we collected spectra of about 500 objects, of which some of them we found were suitable for other more detailed and higher priority science. But we needed to find those objects first. And so instead of using a small telescope to look at all those objects, we used Gemini on nights when either the image quality was very poor or it was, the clouds were fairly thick, and so not much light was getting through. Okay, then we also have large and long programs. Some programs people may want to observe over objects over a long period of time, over several semesters. Those take up 20% of the allocated time. There's also a fast turnaround program which runs monthly. Every month, 20 hours of time is available. You submit a proposal, gets refereed, and some programs are given time. And then for the following 3 months, those programs can be observed. If they're not observed during those 3 months, then the proposal dies and you have to resubmit it. And finally, the director of the observatory is given time for him or her to allocate on, depending on what he or she thinks is important. And those programs require special proposals. Somebody might have a great idea in the middle of the semester. Oh, this is something we should do. It'll only take a few hours. And instead of waiting for the proposal process to complete, the person can submit a proposal to the director who gets it refereed and he makes a quick decision. So say a very unusual event happens and somebody wants to observe it. That's a way in which that can be handled within a day or two. Okay, in addition to that, all these different proposal classes, there are also different ways in which the programs can be observed. There's the Q mode, which I described before, in which the highest priority programs are done consistent with the weather conditions. There's the classical mode, where somebody comes out and actually does take certain nights. That might be the case if there was a certain phenomenon that's occurring on a certain night or so, or a couple of nights, or that's not always available, and only a small amount of time is usually given to that, where the observers actually come out. There's a priority visitor mode, where a visitor might come out and hope that his or her program is observed during the time that he or she is present at the observatory. And that's a hybrid, where most of the observing during the night might be the normal Q program, but when the object that the person's interested in is up in the sky, that object would be observed. Then there are targets of opportunity. These are objects like, somebody might have been have asked for time to observe a certain type of supernova when it explodes or shortly after it explodes. But of course, we don't know where that target will be. So the person still might say, well, this is important science. The committees might award time to that. And so that proposal is just sort of sitting there waiting for the right type of supernova to go off. And when it does, since it's picked up by these robotic telescopes very quickly, that science team can then decide, is this the supernova we want to observe, or do we want to wait for a better one? And if it's the one they want to observe, they activate their program. And I can be, if I'm the observer that night, I can be sitting at the telescope, and all of a sudden a message flashes up on the screen saying, this rapid target of opportunity is ready to be observed. And basically what that means is that we have to drop what we're doing and observe it. Sometimes we can then, usually call the scientist, one of the science team for that program, and say, well, we're finishing an observation of this object. We need 30 minutes more for that. Do we really need to stop right now and do your program, or can we finish this and then go on? And usually that's the scientist will say, go ahead and finish and then do it. But occasionally they'll say, no, this object is brightening very rapidly or changing very rapidly. We want to observe it right away. And then you just have to stop what you're doing. And then you can also ask for the option of eavesdropping, where you're sitting in your office in some other part of the world, but you can actually follow the observations remotely. You can be connected into the control room and see what's going on. So there are all these possible ways in which objects can be observed, types of programs and modes of observing. Next slide, please. Next slide. There we go. Whoops, that's the wrong way. You're going backwards. Okay. All right. So you don't need to look at all of the information here, but basically every observing proposal must include the minimum weather conditions that would be required for it to be completed. And there are a number of weather conditions that are important. One, of course, is the image quality. And that's the sort of the possibilities are in the columns on the top left of what we call 20 percentile image, 70 percentile, 85 percentile, and any. So 20 percentile is the very best seeing, and the full width half maximum, the visible or the infrared size of the object or seeing image is listed in the column below. On the right is you have to specify how much cloud you can tolerate. Some programs, like the poor weather program I was telling you about, can take very, very thick cloud. Some people require the sky to be absolutely clear. They want an absolute measurement of the brightness of the object, or the object's faint, or the science target is very faint, so they need the best conditions to observe it. Water vapor is very important for infrared observations. At some wavelengths, water vapor is a very strong absorber. So you have to specify the amount of water vapor that you can tolerate above Mauna Kea. And finally, there's the sky brightness, whether the moon is out or not, or how bright the moon is. Some, especially visible observations of faint objects, require dark skies, whereas most infrared measurements, it doesn't make any difference whether the moon is out or not, because the infrared light from the moon doesn't scatter over the sky like visible light does. So all of those must be specified, and each partner country has to allocate its time among a range of sky conditions, because it wouldn't be fair for a country to give only time to the programs that needed the best weather conditions. That would take all the good conditions from the other partner countries, and we know those conditions don't occur most of the time. So to give everybody a fair chance, each partner's country's allocation must distribute its accepted programs among a range of sky conditions. And then Gemini will observe the programs in the minimum conditions or better. So if your program is accepted and is observed, you will get observations under better weather conditions than you either just as good as just as the conditions you asked for, or better weather conditions. So all these things get folded into what we do on any night. If you go to the next slide, and you'll see what the result of that is. How am I doing for time? Okay. Okay, so here during each day, one of the astronomers at the office makes up plans for observing the following night, depending somewhat on what the weather conditions are expected to be, but for a different range, for ranges of different weather conditions. And so that's what these plots show. Each of these show what would happen during the night. Now, what you see here, this graph, you can see the y-axis is the elevation of the object, and then the horizontal axis is time. So on the left is sunset, and it goes through the night and on to sunrise. And each of those bands is an observation, the one with the numbers on them. Yes? Hello? Somebody asking something? So the dark shaded bands are the actual science observations, and the lighter shaded ones are calibration stars and so on. So you can see on the top plot, you can see there are probably about 20 different observations during the night. That's if the weather is poor seeing but clear sky. So the seeing is probably more like 1 arcsecond instead of 6 or 7/10 of an arcsecond or 2/10 of an arcsecond. So those programs could tolerate the poor seeing, but they needed clear sky. And those are the highest priority programs consistent with the conditions, with those sky conditions and the instruments that are on the telescope at the time. The lower one shows a plan for the same night, but this is if there's thin clouds and the seeing is what's called poor, what we call poor. And there you can see one very long observation that takes about, I guess it takes about 3 hours near the beginning of the night, and then a bunch of shorter observations. So which one is observed depends on the conditions. So when you start the night, we know how much moonlight there's going to be. We know how much clouds. We can tell how cloudy it is. We have monitors for that. We know how much water vapor is above the sky. We have a way of measuring that. What we don't know is the image quality. And so the first thing we do is we point the telescope to a bright star, and we tune the primary mirror and everything else to get the sharpest images possible and see what those image sizes are. And that tells us then we have all the information as to the seeing and all the other information, the water vapor, the sky brightness, the cloudiness, and then the observer can select a observing plan. And if during the night things change, the atmosphere gets wetter or drier, or the seeing gets better or worse, then you might drop that program and pick up another program, because there are about 6 or 7 of these for different weather conditions during the night. So you can drop one program and you can start doing another one. And of course, if there's a rapid target of opportunity that comes up, that messes with the plans as well. So all those things go into what happens during a night. And then the next day, the astronomer at the base who's responsible for setting the programs knows what's been observed and comes up with new programs. This sounds very complicated, and it is, but we have very good software tools to help the observer on the ground, the server at the office, set up these observing plans. Okay, next slide. Okay, so here is the control room in Hilo. As I said, about five years ago, we went from having astronomers actually up at the telescope during the night and a telescope operator up at the telescope to running things from Hilo. That's a lot more comfortable, because working at high altitude at 4,200 meters is not easy on the body. Although I seem to have done very well there, and I actually love being on top of the mountain. I'm glad I was an active astronomer at the time when you actually had to be at the telescope to observe. But this is certainly a lot more comfortable. So in the background is the guy who's running the telescope using those computer screens, moving the telescope from one object to another, helping identify the object, making fine adjustments to say, put the star in the slit of the spectrograph. And then in the foreground are the scientists who are actually controlling the instrument, deciding which object, which program should be observed next, and running the instrument, say the infrared spectrograph or the visible camera or the infrared camera or whatever, to take the data. I was in my own presentation, I was then going to go on and show you what the observing tools that are used to do that, some of the observing tools, but we don't have that in the presentation that Amar has. So let's go on then to the next slide. Okay, so as I said, each partner country and the University of Hawaii has its own time allocation committee, and each one decides which programs are its highest priority ones. Each one receives its own applications for telescope time. So for example, Chile gets 10% of the time at Gemini South, and it decides how that 10% of the time is going to be allocated, and it prioritizes them scientifically. And as I said, the programs have to cover a range of weather conditions. So each country has a priority list. Those get merged in by the Gemini staff into a single list of programs, and this is part of that list. There are 100, for example, this semester that we're in now, there are 130 programs that have been accepted and could be observed if the weather were great all semester and everything worked well. And you can see these are just the names of them. If you look partway down, there's one called about a little bit below the middle. It's called On the Nature of an X-ray Runaway Star. So we're going to look at that program in a little more detail in the following slides. But anyway, so there are most of the programs are Q programs. There are 45 programs that were given highest priority, Q band 1, 33 given medium priority, 29 given low priority, and the rest were all rejected. Then there are 5 active large and long programs that run over several semesters, but for which some of the observations would be done this semester. There are 26 fast turnaround programs that have been given time, but there will be more as the semester goes on. And then so far there's been 7 director's discretionary time programs that have been allocated time to observe special events or special objects. Okay, next slide, please. Okay, so here's if you want to telescope time at any observatory, you have to write a proposal. So here's the proposal that I was talking about on the nature of an X-ray runaway star. So this is at the top is the list of scientists on the proposal. You can see the principal investigator is at Jet Propulsion Lab at Caltech, but the co-investigators, there are 2 at the University of Southampton in England. There's 1 in Thailand, and those people are all collaborating on the science of studying this X-ray runaway star. I guess I'm not an expert in this field at all, but runaway stars are stars that are moving through the galaxy at very high speed. Some of them may be ejected from the galaxy. Often that's because of say an encounter with a black hole that accelerated the object to high speed, didn't tear it apart, but sent it to high speed. This is a high velocity star that is an X-ray source, and that probably tells you that it has a companion, that it's a binary system. And so these people are asking for time to measure its spectrum at a number of two epochs, I guess, to measure the mean radial velocity, and to look for wobble, changes in velocity, which you would see if this is actually a binary and the 2 stars are orbiting one another, the spectrum would shift back and forth a little bit. So this proposal got time. It asked for 4 hours, and I don't know how much time it was given, but that's what it asked for. So you can see abstract is sort of a short description of the program. The next slide shows more details of the program. Okay, so here are the observing details, the name of the object. It's a Gaia star. Its position in the sky is given, its brightness, how much time is needed, and then the weather conditions you can see. CC 70 means thin clouds, IQ 85 means poor, sky brightness 80 means some moonlight, but not very much, and they didn't care how much water vapor there was above the atmosphere. And then they were using GMOS with its long slit, with a certain grading and so on, and a certain slit width, and they need 3.98 hours total. I think 3.6 is for the observations and 0.36 is for calibrations. And then they have to give a much more detailed scientific justification, and this is only part of it. Anyway, all those proposals go to a committee. The committees for Gemini are actually meeting right now and deciding who gets time for the semester 2024B, which will begin in August. The awards of time will be announced in early June, and each program will then, the scientists in each program will work with Gemini staff to set up the observations that they need. And once those observations are set and declared ready, then they can go into a nightly program starting in August, and that semester will run from August 1st to January 31st of 2025. This is a proposal that is running from February 1st of this year to I think July 31st, the end of semester 2024A. So this program, I don't know whether it's been observed or not, but the source is actually up now in the early evening at our RA of 14 hours, which means it's probably in the west and sets maybe around midnight or something like that at this time of year. So there's still plenty of time to observe it if it hasn't been observed. Okay, next slide. Okay, so once the data are obtained, they're owned for a while by the science team that made the proposal. So they can access the data, and we can access it. We Gemini staff can access it and help them, say, review the data, help them reduce the data, and so on, and turn it into publishable form. But they only have access to the data for a year for the Q observes and for the classical observing. After that, I mean, it's accessible to them after that, but after that, it's accessible to the entire world. So any one of you could go into the Gemini archive, create your account, and pull out any data that are more than 1 year old from these Q observations. For some of the observing modes, the proprietary time is even less than a year, 6 months, for example, for the fast turnaround time. So there's no, I mean, there's a privacy for a while because everybody wants to, scientists want to have time of their own to figure out what they've observed and what it means and write a paper about it, write papers about them. But after that, the data are available to anybody. Next slide. Okay. Well, finally, so that really more or less concludes my talk, but I just wanted to say that, that these telescopes are complicated instruments, and we scientists benefit from the work of a whole bunch of people. If you run this movie, you'll see one of the more complicated aspects of running a telescope, which is recoding the primary mirror. Every few years or so, we have to take the primary mirror off the telescope and re-illuminize it. If you run this movie, Amar, then you can see sort of in a few minute sequence, can you run it? There should be a start movie bar down at the bottom. There we go. Okay. So this is a 4-minute sequence covering about 4 or 5 days, in which engineers from, actually, sometimes engineers from both telescopes are involved. So say the engineers from Gemini North would fly down to Chile, some of them, and would help with the procedure. So the instruments have already been taken off the primary mirror cell, and they're now taking the primary off the telescope. Here it comes. It looks nice and clean, but it's actually very dirty. So they now have to lower it down to the ground floor, which is where the cleaning takes place and where it will be recoded. So that's the thin meniscus primary mirror, 8.1 meters in diameter. As they lift it off, you'll see some of the actuators underneath which control its shape. You'll get a better view of them later on. Lifting this mirror. Now they move the mirror cell out of the way, and then they can lower the primary mirror down to the ground floor. So they're just hanging there. Now they bring something to hold the mirror. Okay. Okay, now they've put it in this mirror holder, and now they're getting ready to clean the mirror. And of course, you can't walk around on the mirror cleaning it. You have to have access to it without touching it. So I believe they're probably spraying a sodium hydroxide solution. That's what I used to use when I was a graduate student to clean the little mirrors that I made for the spectrographs I helped to build. So that dissolves the silver or the aluminum. They've washed it once, they washed it twice. Now they're gonna put it into the coating chamber. So they remove the bottom of the coating chamber, which is a big container which they will evacuate, pump all the air out of, and then they will deposit a layer of aluminum or silver or so on. It's going into the mirror, into the coating chamber. And now we're looking into the coating chamber, which has been pumped on, but the air's been pumped out of it for probably a day or two to get it down to low pressure. And then you evaporate or you sputter aluminum or silver onto the mirror. You can see as the mirror is being rotated, it's being coated. And here it comes, a new freshly coated mirror. Now they have to bring it back up to the dome floor, which is up on the 5th floor of the dome. Here it goes up. There's the bottom of the mirror cell with all the actuators you can see that push on the mirror to keep it in the right shape as the telescope moves. So if it weren't for all these engineers and machinists, secretaries, administrators, and many other people, we scientists would be lost. So we're the beneficiaries of a lot of work by lots and lots of people. The staff at each of the observatories consists of about, I think, 75 or so people, and only about 15 or 20 of us are actual scientists. The rest are doing electrical engineering, mechanical engineering, and so on. Every day during the week, there's a crew that goes up to the telescope, changes instruments that need to be changed, does other maintenance work in the dome, repairs anything that's broken, and so on, so that the telescope is ready for the next night. So, okay, go on to the next slide. I think that finishes my talk. I was going to tell you a little bit about some of the science that we do, but I don't think I finished preparing those slides in time. You can go to the next slide if you want, and let me see. I don't remember what. Yeah, okay. So I didn't finish these slides, unfortunately, until this morning. But one of the programs, I've told you how amateur astronomers are very instrumental in helping professional astronomers study objects. And one type of objects that they have spent a lot of time monitoring are a class of objects called our Corona Borealis stars, and that's our Corona Borealis there in the constellation Corona Borealis. It has an amazing light curve. It sits pretty much at a certain brightness for a month or even years at a time, and then suddenly it drops down and is maybe 1,000 times fainter than it was just a few days before that, and then it slowly regains brightness. And it's understood now, pretty much understood what happens, that this star has a wind coming out of it. As the wind cools down, dust condenses around the star, and that makes the star dimmer. Then as the dust dissipates, it gets brighter. What we have found is that these stars have an amazing abundance of a very rare isotope of oxygen, oxygen 18, which is just as abundant in these stars as oxygen 16. In interstellar space and the sun, in most stars, oxygen 18, a stable element, isotope of oxygen, is only about 0.2% of all the oxygen. Most of the oxygen is oxygen 16. So these stars have had something go on amazingly that have somehow managed to create oxygen. a lot of oxygen 18, and it's now believed that the process that these objects that look like stars are actually the result of mergers of two white dwarfs. And during the merger process, which heats up the surface of the more massive white dwarf, a lot of nuclear processing goes on and a lot of oxygen 18 is made. So I've been involved in that research, many other kinds of research as well. But that's one class of objects where amateur astronomers have provided a lot of useful information. So let me stop there. Thank you so much for your attention. This has been a lot of fun. I'm sorry I wasn't able to show the slides myself, but thank you, Amar, for doing that. One thing I wanted to say is that you might not want to know, you might want to know just how this talk came to happen. Well, my daughter and her family have been living in Jordan for 3 years, and I've been there several times to visit. And a few days at the most recent visit, I gave a little talk to my youngest granddaughter's school class of 5-year-olds. Unknown to me, her teacher, uncle was Ahmed, who was a member of the Jordanian Astronomical Amateur Astronomy Association, and she told him about me. He invited me to come to the house where I met Amar, the president of the Jordanian Astronomical Association, and that's how this talk got organized. So I've really enjoyed my time in Jordan. Unfortunately, my daughter and her family are moving back to the United States soon, and but I visited there 6 times during the last 3 years, and I love that. I love your country, and I hope to come back again, whether or not my family's there. So thank you so much, and if you have any questions, I don't know what time it is, but I'm happy to answer questions. Thank you.
Thank you so much, Dr. Tom, for this wonderful presentation. I have really enjoyed it. So now we can have Q&A. إذا حدا عنده أي سؤال أو تعليق ممكن برفع الإيدين على الزوم أو من خلال الناس الموجودين في القاعة. بسمة، أستاذة بسمة معنا.
Hello.
عمار.
Hello.
نعم تفضل.
First of all, thank you so much, Dr. Tom, for the nice talk. Really, I love it.
Thank you.
It's really huge telescopes, and it's the largest one. We are talking about 10 meters and 8 something meters, which is a huge one. So this is a good opportunity for us to hear about this high sophisticated advanced telescopes. So right now we are so happy we meet you first in Jordan a few weeks ago, and right now it's our pleasure to invite you again to Jordan and have face-to-face talk next time, inshallah.
Thank you. Thank you. I would love to come back to Jordan. If I do, I will certainly look forward to seeing you, and I could be happy to give a additional talk or two about about some of the science that I do, about some other astronomical issues. One thing that we had a staff meeting the other day, and I mentioned I was giving this talk to the amateur astronomers in the Arabic world, and one of the scientists who runs a program where people can actually watch during the observing suggested that we set up a remote observing night with amateur astronomers in the Arabic world. That would be during the daytime, your time, but in the middle of the night at Gemini in Hawaii, in which you can actually see the observing taking place. I can tell you more about how it works, and I think you'd really enjoy seeing how we actually carry out the observations. Pictures are one thing, but actually seeing it live and talking to the observers is another thing.
My question about the visit to enhance the scientific collaboration, because we have some professional astronomers here in Jordan, the Arab world. And how about to enhance such a scientific collaboration by first visiting these telescopes and start doing research with you or with your colleagues on huge or large telescopes? What's the process for a visit Hawaii telescopes. And if you want to start,
in principle, anybody can come visit the telescopes. They're not available at night. Of course, there's nobody up the mountain and there's safety concerns, but during the day, there are tours of the telescopes, of our telescope.
yeah,
When I have friends visiting and they want to see the telescope, what I normally do is I drive them up to the mountain to watch the sunset, which is gorgeous. And then we drive back down to Hilo and we go into the control room and watch the observing taking place. But if somebody actually wanted to do science, you would probably need to explain what that science is and see if we can write up, see if we could work on a proposal together. That proposal would be submitted to the committee, probably be asking for time, U.S. time, since I'm a U.S. citizen. And then we just have to see. I should say it's not easy to get telescope time. The oversubscription factor for the Gemini telescopes is about a factor of 3, which means that only 1 out of every 3 programs gets time. So I've had lots of proposals some accepted, lots of proposals rejected, with comments from the referees about, sometimes it's just, well, this is a good proposal, but there's too much demand. Sometimes there are flaws in the proposal. So sometimes you can then improve the proposal for a future semester, resubmit it and get time again. But it's no, there's
like,
no
publishing a paper, right? Like publishing a scientific paper.
Yes.
Yeah. I have a question here. I mean, for citizens, non-American citizens, that is, can we apply for serving time?
Yes. You can. For a number of the partner countries with only small amounts of time do not allow that, but the United States does allow anyone to apply for time. And of course,
Okay.
yeah. So, if you were interested, I could send you some sample proposals. You could see how they have to be written. There's a limit. You can't write pages and pages about it. You have to keep the proposal down to 1 page, and you can submit supporting figures and so on. And you have to estimate how much time you need and weather conditions and so on. So
I'd appreciate it if you send me this information.
Okay. I'll probably send it to Amar, since I don't know your email address.
No problem.
You can also look at the Gemini. You can also look at the Gemini website, and you can see what the proposal process is as well.
Okay, thank you so much, Tom, for this beautiful presentation. It's amazing, really. Now we have a question from Anas Sawalha. Anas is a doctor. He is a dentist, but he is a good astronomer too. Yes. So please, Anas Sawalha. Anas,
can you hear us? تفضل أنس.
الو
الصوت المايك.
Unmute, yes.
صوت مسموع.
good.
نعم
تمام.
First,
I would like to thank Dr. Tom for this beautiful presentation, and I would like to thank as well the Jordanian Astronomical Association for this talk as well. My question is that I don't know what if I will get it right or wrong. My question is regarding the IFU spectrograph. We all know that NearSpec on James Webb has an IFU module, which takes a spectroscopy for each pixel. My question is that what is the minimum angular size of a certain object it should have in order to get two separate spectra of different locations on the same object?
I'm not quite sure what you're asking, but the field which instrument are you talking about?
I'm talking about the IFU spectrograph on Gemini's telescope.
Okay, you're talking about
the object needs to be has a certain size in order to get two different spectra.
That array has about a field of view of about 3 arc seconds by 3 arc seconds. So, for example, you could fit Titan, the Saturn, easily into that. For something like Jupiter, you would just have to look at a small patch of it, like you want to look at a hole or something like that.
So So if the object has, for example, like 9 arc seconds angular size, you can take different spectra, three different spectra of the same object.
You can move it from one place to another. Yes, take spectra.
Yeah, yeah. Oh, okay. Thank you, Dr. James. Thank you.
You're very welcome. Yeah.
اوكي بس ما في حدا من عندك بده يسأل. في عنا دكتور سعيد طباغ، تفضل دكتور سعيد.
He's muted, I think.
دكتور سعيد سامعنا؟
No, the mic is working. Good evening.
Good evening.
Thank you for your presentation. It was great presentation. I have question about the sodium layer.
Yes.
And how we can get the data of this layer, because it's connected with atmosphere also.
Yes, it's a debris left over from meteors and meteorites that have entered the atmosphere and have slightly, been heated, and some of the material has evaporated off come off the meteor, and it's sitting at that altitude. Most of it's sitting at that altitude. Of course, there's sodium everywhere, but there's a lot more at around that altitude for reasons I don't know. So that when the laser beam strikes those sodium atoms, it excites them, and then they re-emit. And most of that emission goes off in other directions, but some of it comes back down directly from where the laser passed through, comes back down. So that's why you see what looks like
maybe you can measure the height of this layer.
It's about 90 kilometers above the ground. It's about 90 kilometers above the ground. And because it's not out at infinity like the stars, the adaptive optics can't do quite as good a job in correcting. If it corrects for that, it's not correcting quite properly for the stars, which are out at much larger distances, but it does a pretty good job of correcting.
What's the thickness of the layer?
What?
The thickness of the layer.
Oh, the layer. Oh, I think it's just a few kilometers thick. Why that is, I don't know. I'd have to look.
Nobody knows. Just for that,
for some reason, that's where the atoms are. Maybe at lower altitudes they combine with other elements to form compounds, and then they don't work. So that's a place. That's an altitude where the atoms are still free, not part of molecules.
I guess it's still open question about this.
Well, it's probably understood, but not by me. I'd have to look. But it's a very useful
also
tool.
About the oxygen, you mentioned about oxygen 18.
Yes.
About the isotopes of oxygen.
Yes.
What do you think is the real conditions to produce
to create the oxygen 18?
Nuclear physics?
Yeah, there have been these are corona borealis stars, and their cousins, which are called hydrogen deficient carbon stars, which are the same elemental chemistry and makeup as our corona borealis stars, but they don't vary. These are believed to be the result of the merger of two white dwarfs. Now, you might think, what is the likelihood that two white dwarfs would collide and merge? Doesn't sound very likely, but you have to remember that lots of stars are binaries. And so you can imagine a situation where a fairly close binary forms. One of the stars eventually evolves into a red giant once it leaves the main sequence. And when that happens, the other star finds itself inside the envelope of the red giant, and that friction brings the two stars closer together. Then that red giant turns into a white dwarf eventually once it loses its outer layers. And then eventually the second star becomes a red giant. The lower mass star becomes a red giant at some later time, and then the same process happens. So the two objects turn into white dwarfs that are very close together, and then by gravitational radiation, if they're close enough, they will eventually spiral into one another and merge. And of course, that's a cataclysmic event. It creates a lot of heating. What happens is that the higher mass white dwarf basically shreds, tears apart the lower mass white dwarf, some of that material gets ejected. No one's ever seen this happen, of course, but because it's very rare. But we believe that these are coronal borealis stars and hydrogen deficient carbon stars as a result of that. And during that heating process, all sorts of nuclear reactions take place. Now, white dwarfs are mainly, they've lost their outer layers. Their inner layers are mostly carbon, nitrogen, maybe some oxygen, and various nuclear reactions take place. One of the ones that can take place is that a helium nucleus can combine with nitrogen-14 to create oxygen-18. That happens very, very easily at a certain temperature, of I don't know how many millions of degrees, many millions of degrees. At higher temperatures, the oxygen-18 that's created will react with another helium nucleus to create neon-22. So what we think happens is that during some of these mergers, the temperatures reach the level where the first reaction creating oxygen-18 occurs, but then it cools off before the reaction that destroys oxygen-18 can take place at a and so what's left is that there's lots of oxygen-18 left in the outside of these white dwarfs. Some of it gets expelled and turns into kind of an atmosphere. So our coronal borealis stars kind of look like red giants because these mergers create what looks like a star, but it's really at the center of the star is a white dwarf, and the outer of the star is the product of the merger. And so this is still somewhat controversial, but it seems to be the only way which you could explain such a very strange isotopic abundance ratio, where oxygen-18 is as abundant as oxygen-16. In fact, we found some of these stars where oxygen-18 is more abundant than oxygen-16 by a factor of 2 or 3. So it's a very unusual thing, and it just points to something very energetic happening. And there were other ideas about how our coronal borealis star was created, and those involved just a single star, but there doesn't seem to be any way that a single star would do something like this, produce all this oxygen-18. Does that somewhat explain what you were asking?
Thank you very much.
You're welcome.
Yeah, we have a question here.
Oh, hi. Thank you, Dr. Geballe, for your lecture, valuable lecture. And my question is about, surely Gemini Observatory had collected too many astronomical data. My question is, what is the most distinguished discovery were made during the last year?
Oh my gosh, there's so many. I mean, there are hundreds of programs being done. Of course, everybody thinks their science is distinguished. I think one of, let's see, what can I say? Oh my goodness. I have to think about this. I mean, actually, what I'm thinking right now about is something that some of the other telescopes were more involved in Gemini, and that is measuring these very distant supernovae, which are used as sort of standard candles to measure the expansion of the universe, and the discovery that our universe, the expansion is actually accelerating. That was actually done mostly at the Keck telescopes and with the Hubble Space Telescope, and so Gemini hasn't played much of a role in that. Gemini has played a role in studying the black hole at the center of the Milky Way by helping to measure the positions and speeds of some of the stars that are orbiting that black hole. At the center of the Milky Way is a black hole with a mass of about 4 million suns, and there's a cluster of stars that are orbiting it with orbital periods of 1 year to a few years, and those have been used to estimate the mass of the black hole, and in fact determine that it is 4 million. Yeah, so that's been one very important measurement that Gemini, along with several other observatories, has participated in.
I've read
Thank you, Mr. Tom.
in physics, right? To a group of astrophysicists, Dr. Gaze and her colleagues. A few years ago, they received the Nobel Prize in Physics
That's right.
on this
Yes.
topic.
Yes, Dr. Gez and Dr. Genzel. Yeah. Yeah.
Exactly.
Yes.
May I
Thank you, Dr. Tom. Thank you very much. And we are looking forward to see you here in Amman.
All right.
You are the most welcome here in our homes and in our hearts.
Thank you. I'm going to have to come back, even if my family isn't there.
I have a question. Excuse me. Since you have certainly have very large amounts of data in your archives, has any astronomer or data scientist used, let's say, AI methods in this analysis, in analyzing the data?
Not that I know of. That's a new field that's just getting started. But certainly other people have, I guess you'd say, mined the data that were obtained by others, old data, to learn new things. But I don't know that they've used AI to do so.
Okay, fine.
That might be used for a telescope that's doing survey work. To find, I know there have been, there are surveys that have been done, created huge amounts of data, and astronomers have asked for help from the general public to identify new kinds of objects, and that has been very successful. And I'm sure AI could play an important role in that. But it's been amazing what the general public has done. They log in, they look at these images, they find objects. There's a certain class of galaxy called the green pea galaxy, and the first example of that was found by a second-grade teacher in the Netherlands. Who found this object, called attention to one of the astronomers who was involved in setting up the survey, and that has resulted in a lot of science. And that object is known. That object is known by the name of the first name of the teacher. I speak Dutch, so it's called Hanni's voorwerp, Hanni's object.
Okay, that's really interesting. So that's really interesting to let our public get involved in such citizen science projects, right?
Yes.
I mean,
they're available. I don't know the details of how you do, but I'm sure if you just Google citizen science, you'd find a whole bunch of them.
Okay, very good. I think Dr. Anas has raised his hand once more. Fadlan, Dr. Anas.
I got another question, Dr. Tom, about the laser used for adaptive optics. From what I understand, that you point the laser to the sky and it creates some sort of artificial star. My question is that, does it get turned off? Then you take the adaptive optic things, or just it stays on? I don't know what happens
next. The laser is continually emitting, so we don't use the laser guide star for everything. So it's normally turned off. We also have to be aware of planes flying overhead. So if there's an airplane flying overhead, we have to turn the laser off. So every night we are in touch with I can't remember, it's some military group that, and also they don't want us to shine the laser on any satellite, especially ones that have military implications. So there's all these rules about when we can use it. But for the most part, we can use it almost continuing all night, except for maybe a few instances where it has to be turned off for a few seconds. But of course, the laser isn't used for all science. As you saw during that video, that night it was only used once or twice, and most of the night it was used. It wasn't needed. I think the Gemini South telescope has a lot more problems with its laser system because there are lots of planes flying from Santiago, Chile, to cities in the northern hemisphere, and a lot of them pass over that mountain where the telescope's located. So they have a lot of problems, especially early in the night when the planes are just leaving Santiago, and toward the end of the night when the planes are arriving in Santiago, they pass over this telescope. So they aren't able to use it as much as they'd like to. Let's put it that way.
Thank you very much.
Sure.
Okay, Dr. Hanna, before we can have a nice picture with all the audiences on Zoom and here in our association, there is a question from one of our friends. He or she, I don't know. asks about the most challenges regarding the atmospheric conditions in Hawaii.
The
Is
most
it
challenging?
possible? Is it, yeah, about the climate or the atmospheric conditions regarding the astronomical events?
Yeah. Well, there can be all sorts of things. I mean, you can have weather. I think the hard part is the most frustrating part is when it's almost good enough to observe, but not quite. So I would say that the humidity at the summit is major frustration. Sometimes we are supposed to close the dome if the humidity arises above 85%. And then we have to wait. If it drops below that, we have to wait for 30 minutes or an hour to make sure it stays below, because it's so important not to get moisture onto the primary mirror. So there are those nights when the humidity is hovering around 85%, and you really want, and it's perfectly clear outside, and you really want to observe, but you can't. You're not allowed. The telescope operator who's in charge of the safety of the telescope won't allow you to. So I'm not blaming the operator. He's just protecting the telescope. But those nights can be very frustrating. And there are other nights when, of course, the weather is horrible and there's no question you can't observe. And at that point, sometimes you know the weather's going to be bad all night, so you might as well go home and go to bed. So those nights are those happen, but those aren't so frustrating. Of course, another frustrating thing is when there's a event, for example, an occultation. There's a star that's, say, occulting, that's passing behind Pluto, and so this happens at a specific time, and so that program has to be observed at that time. The person may want to be, study how the star dims as it passes behind Pluto in order to understand something about the atmosphere of Pluto, but the weather's bad at that time, so you can't take the data on that. So that opportunity is just lost. Those can be very frustrating. Other programs, if the weather's bad, no problem, you can observe it the next night or next week or whatever. But so those are two very frustrating things about being an astronomer.
Okay, Mr. Tom, it's our pleasure to have you in an astronomical event here in Jordan, in our camp in Al-Azraq Desert or in Wadi Rum. So you are welcome always.
I've been to Wadi Rum. I love it there. I love being out in the desert at night. And I actually gave a little impromptu talk when I was staying there to the other tourists who were there. We all walked out and looked at stars, and I talked a little bit about a white dwarf. Yeah.
Okay, good.
Yeah. One more question, Tom. Would you please just give us an idea about the site selection when you use Hawaii, and have an idea about the site selection of choosing the places for a larger telescope like this?
Yes. Well, these days, of course, sky brightness, or being away from cities, is very important. Seeing is very important. Altitude is important. So all of those things go into deciding what sites are selected. And Mauna Kea, I think overall, is the best site. Certainly in terms of image quality, it's the best site. There are actually sites in the Andes which are even better in terms of less water vapor and maybe even colder. But because they're inland, their image quality is not quite as good as Gemini's. Of course, adaptive optics can correct a lot for that. So there actually are some much larger telescopes that are going to be built. The Europeans are building a 39-meter telescope in the Andes foothills. The U.S. wants to do the same thing in the northern hemisphere. And the site of choice is Mauna Kea, but that telescope, because of some political problems and other issues, construction hasn't started yet. So the U.S. astronomy community is very worried that the Europeans are going to get too far ahead of us.
Great. One more. Just have an idea about the dark sky meter. How important in the top of the mountains?
Say that again.
The dark sky meter. I'm asking about the portal scale. at the top of the mountain.
The
One
darkness?
portal, three portals. What's the number of portals in the top of the mountains?
Number of what?
Portals. Dark sky meter.
You mean measuring how dark it is?
Yeah, to measure the darkness.
Oh,
We use
well,
to measure the darkness of the sky, yeah?
yeah, I don't know how it's done, but it is it must be easy for any optical camera to do, because if you take an image of the sky, you see how much background there is away from the stars, so you can
In
measure.
Jordan, we have 2 to 3. Yeah, most of places have 2 to 3 portal. It is the dark sky here. But I'm asking about the top of mountains. If you want to have an idea about that,
Whether it's darker than other places? Oh,
yes,
I
the
see.
dark.
So I don't really know, but I know that I don't think I can answer that very well. I know that people have been monitoring the sky brightness on Mauna Kea for some time, and as the population has grown, the sky brightness hasn't really changed very much. So on a dark night, it's still just about as dark as it was, 10 or 20 years ago. But I don't know the absolute measurements. I mean, they do exist. They're probably on the Gemini website, but I don't know what they are. I'm sorry.
Okay,
No.
thank you so much, Mr. Tom. Now we want to have a photo with you. Please يا جماعة كل الأصدقاء معنا على الزوم واللي موجودين الآن اللي موجودين معنا رح نوقف على الشاشة.
الكاميرات.
اوكي رح ناخذ دكتور حنا رح تفتح من عندك تاخذ
رح نوقف. Hello from the people here at the hall. Hello, Tom.
Well, hello to all of you. I see a lot of names and pictures.
يفتحوا الكاميرات عشان ناخذ صورة جماعية. رنيم، هاني، دكتور أيمن بطاينة، كالتشرال سنتر، رامي سعادة، أستاذ محمد رضوان، يوسف شيشاني، أستاذ محمد ميقاتي، دكتور رماح المصاروي. يا ريت إنه تفتحوا الكاميرات إذا بتحبوا عشان ناخذ صورة جماعية.
اوكي جود. دكتور حنا رح ناخذ ضيفنا. احنا رح دقيقة احنا رح نوقف جنب الشاشة الكبيرة كلنا.
My wife Carol.
ناخذ الصورة معكم. يس. اوكي هاي.
هاي.
Okay. Goes back to Jordan. I will come with him.
They are most welcome.
We made a lot of very good friends.
كمان صورة full screen هيا.
دكتور حنا بخلي الدكتور توم يحكي عشان هو يطلع بوسط الصورة.
كيف؟ تمام تعملي. راح الصوت بسمع مايك.
عم نضبط الوقفة بس. يلا اوكي. رنيم رح تصور واحنا هيك عم ماخذين اخراج معين. دكتور انتم مخربين على الشاشة اللي ورا. رنيم مبين الشاشة؟ مش مبينة.
اوكي جاهزين؟
Oh, I see a beautiful
1 2 and 3. تمام. كمان واحدة. 1.
Please again. Excuse me, Dr. Tom. خلينا نسمع توم.
موجود. 1 2 and 3. خلص تمام. أخذنا أكثر من صورة. إن شاء الله بنبعث لكم إياها. So, Dr. Tom, I don't know how to thank you for this interesting lecture and presentation. I really enjoyed it. Everybody has enjoyed it, and let's keep in touch. And maybe we'll host you soon in live in Amman in a live lecture.
That would be wonderful. This has been a total pleasure for me.
I think last word from Khalid Tel. Khalid, do you hear me?
Yes. Hi, Khalid.
Khalid with us.
ما عندوش mic. His mic is muted.
I open it. Khalid, do you hear me?
Yes, I can hear you now. I was trying to.
Yes.
Hi, Tom. How are you? It's nice to see you again.
Thank you for having me at your house. And
no, Tom, welcome. It's always open for you anytime, my friend.
all right, I hope to
We're
take advantage of
looking
it.
forward for your next visit to meet you. Hopefully, it was nice big lecture. I'm sure I missed most of it. Sorry, but it's my pleasure to catch you at the end.
Okay, well, it's a recording of it, so you can watch it.
Yeah, sure.
Thank
Sure,
you.
it was my pleasure to arrange it to Jas and Dr. Ammar and to have you. And since we discussed this along your visit in Jordan in my house, so I know the topics that you talked to the guys.
Yes,
I know it was interesting to them because it was interesting to me. Thank you again for your time and for your knowledge that you shared with us. It is our pleasure to have you, and hope that we can have you again in the future, live also.
You're so welcome, and it's just an honor to be able to speak to so many enthusiastic astronomers and other people in a world that's quite distant from the one I live in, and it's been a wonderful experience to learn about Jordan. I love your country, and I look forward to future visits.
You're most welcome to anytime. Wish you all the best. Thank you very much. Thank you.
Dr. Tom, excuse me. There's a question. I just received it on the chat by Zumana. May I ask this question?
Sure.
It says, thank you, Mr. Tom, for these valuable studies. My question is, here in Jordan, we have areas from which you can observe the sky, such as Wadi Rum, for example, which is an area far from population movement. Why are these telescopes not distributed to different regions of the world, especially third world countries, instead of placing them in one region, especially third world countries, and participating in studies, astronomy, or organizing special courses for young students and lovers of astronomy that talk about types of telescopes and how they work, so that astronomy becomes more enjoyable and this science becomes more widely available to everyone, whether a young person or an adult amateur. Okay, that's a question by Zumana.
That's a real problem. Of course, astronomy is an expensive research area. Telescopes are expensive. People want to, the countries, the governments that support astronomy want their telescopes to be on the best possible sites. There are lots of dark sites, which is one criteria, but the other criterion is image quality, water vapor, things like that. And so that may be one reason why some of the big telescopes that are trying to do many kinds of astronomy select specific sites. On the other hand, these days, a small telescope with a good camera on it with lots of pixels can do wonderful astronomy anywhere in the world. And so there are lots of small telescopes. They tend to be clustered at observatories just because of the infrastructure needed to live there and to work there. It's useful to be at a place where there's lots of facilities already available. But there's no reason why, these days, if you see what amateur astronomers are doing, for example, they're doing amazing things with small telescopes and good cameras. So I wish it were the case that there were telescopes everywhere, but I hope that happens at some time in the future. But there are a lot of considerations that have to be made. But yes, astronomy is a wonderful field. Lots of people get into science from astronomy. They learn about science by learning about astronomy, and then they go into other fields. So it's a gateway to many it's a gateway to science in many fields.
STEM, to STEM, the way towards STEM, right, for students.
Yes, STEM. Yeah. Yes, absolutely.
Okay. Then I think we'll have to wrap up now. Thanks everybody for attending this wonderful lecture. And thanks, Dr. Tom, for your this lecture and for your efforts in spreading astronomy to the public, especially when you are talking about a very professional and big instrument like the Gemini telescope.
Yeah. Okay. I'd love to come back sometime, or give another remote talk about some more about the science than the observatory. You know, that you know.
Yeah,
about.
sure. You are most welcome, our friend Tom. You are most welcome. This is
Okay.
a platform. It's for use, and I think we have right now the lecture is recorded. We will publish it in our social media here in Jordan, Arab world.
Okay. Will I be able to have access to that? Because one of the outreach people at our observatory said, please record it.
Yeah, I will send you the link. I will send you the link.
Okay.
Yes.
Great. Thank you so much, everybody. This has been lots of fun. And
Thank you.
Bye for now.
And
Okay.
keep in touch, Tom. Okay?
Okay. We will. Thanks so much, Amar and Ahmed and everyone else.
You are welcome. Thank you.
Bye-bye.
Thank you. Take care. Bye-bye.
Bye-bye.